a software online platform to design your own magnetics from start to finish.
Hey, it's Eamon with ipXchange. We're at day 3 of PCIM. I'm at the Frenetic booth with Sotiris, and they've got a very interesting simulation and hardware solution for designing magnetics. So Sotiris, do you want to take us through the process?
Okay, so basically what we have developed is a software online platform to design your own magnetics from start to finish. So the way we work, like this is a design example for a 3 kilowatt LLC onboard charger, is once you start a new project, then the tool prompts you to this page, which is actually a very simple question about what magnetic you want to design this time. Is it an inductor, transformer, flyback, active flyback? And these are the ready template topologies that we can offer. So you can see phase shifted LLCs, dual active bridges, or something else, something custom. And my colleague Lucas is going for an LLC full bridge transformer. Let's let him take us through the design journey here. So what you see, if you can take a look, this is the waveform tab that we are at. So the goal is to create the excitation waveforms for the magnetic component that we're trying to do, which is the transformer in this case. So possibly you have two options. You can either upload CSV files, as he did, like that, and that takes priority over simulations, or you can go for putting in some basic specs. I mean, all of that specs is pretty known to the engineer right from the get-go, and then he's going to update the waveforms again, and we have the voltage and current waveforms are primary, secondaries, and all of the details needed actually to go on with the design. So the goal here is to create the magnetic waveforms and the discrete Fourier transfer of these and move on. And as you see here, we work in tabs from left to right, so we're in the waveform currently, and Lucas is just playing with different battery voltages, because if you just took a moment, we're going to get back here, but the battery voltage of that onboard charger goes from 250 to 400 volts. So each time, let's say that we have a couple of operating conditions, like the lowest battery voltage charging, the mid voltage, and the high voltage. So he's going to go into the core optimizer tab here, because the first goal in a magnetic is, okay, after you specify what's the currents and voltages, then you need to select a core. Is this big enough? Is this small enough? This is the usual selection. So this tool is going to help you. He selects PQ family shapes, ferrocube 3C95 materials, and a core loss target of 10 watts. So he plots every PQ core that the tool can find. He wants to compare with the E family, so he plots E cores and he plots ETD cores as well. As you see, this is volume versus turns, so the lower the volume, the higher the power density. For automotive application in forced convection, he's going for a PQ50 core, which is very compact. And okay, so he moved on to the second graph. PQ5050 was the selection from the previous graph, and now he's actually plotting the core losses versus turns, because it's time to actually choose the number of turns. The first graph was about choosing a couple of dimensions. I mean, what PQ core works, what exact dimension for the height specification, the power density. The second question is the second graph, that is, okay, I have a couple of actual cores in mind. It's time to select the material and the number of turns. Get it right. So what he's doing right now, he's going back and forth between the core optimizer and the waveform, and he's putting different operating conditions like low battery voltage, mid battery voltage, and high battery voltage, because you will get different power graphs for each steady state condition. So if you want to have a maximum power core loss of 10 watts, then all of the graphs should be below 10 watts specific. That's what he's going to do right in a moment. So 250 volts is about the lowest battery voltage, and the worst operating, I think it's the worst operating condition, as you can see, for the same, oh no, it's, well, that's wrong. It's the best operating condition actually. So you can see all of these graphs for different battery voltages. All right, for 3 battery voltages. And then, okay, we're here. So 250 volts, 300 volts, and 450 volts. If you select the number of turns, let's say 30 turns, which is exactly right this one, you'll see that the core losses is the best you can get is 1.3 watts. If you operate the charger at a higher, once the battery starts charging, the power losses, the core losses are going to raise. How much? Up to 10 something watts. If you take a straight line up, you just see that. So the goal is, in every condition, be below 10 watts. That's the number of turns that you want. Above 30 turns. That's effectively what I'm saying. And he's making now a different selection. So he has an idea now. But he'll do, you see, 3C97 material, 3C95 materials in all 3 cases. Now it's time to see if we can do something better with materials for the worst operating condition, which is that one. So he opts for 3C98, and you can see it's a little bit better for 30 turns. Then he applies it, and you have your basic, all of the specs of the core actually. So ask me any question up to here, probably, because I don't know what everybody's following.
Yeah, I guess a good thing to ask would, I know it comes later, so I'm not going to mention it now,
Okay.
but how many different core materials do you have?
Core materials. So core materials, if you go up here, it's a whole list. So it's a drop-down list. You'll get the whole Ferox tube list, all the 3C something materials, the TDK material list. That's what we have. It's about 35 materials.
Okay.
Or maybe I'm mistaken, maybe it's double that, don't get me wrong. But this is only ferrite. Then you can go for powder cores as well, for inductors, for example, PFC inductors and so forth, which is a whole different list. And then you can add your own material, actually.
Oh, okay.
So if it's not listed, as long as you have the Steinmetz coefficients, that's good enough for the tool to start using the improved generalized Steinmetz coefficient that you
Cool. So if you need something really specific,
you can do it
to your application. Yeah, good.
For materials. Also, you can edit cores. I mean, there is selection of cores, different cores. You maybe had the chance to look the families back in the optimizer, like E cores, ETD cores, PQ cores, planar type cores as well, low profile, high profile. It's all of the standard materials. And okay, right here, everything is actually pre-selected from the optimizer right now. So my colleague is just playing around with the tool just to showcase different capabilities, like, and then we're to the windings part. Okay, so let's just quickly pause here to explain what you see. So the first thing that you see, which is going to be filled with data once he runs it, is a 2D cross section of the bobbin. So you see the core material here, the bobbin material, and then the layers are going to appear just in a jiffy. And basically, we have 2 windings, primary, secondary. This is just a simple transformer. So he's selecting the wires for the winding. You can also, if you are a newcomer, you can also hit suggest wire, and it's going to automatically suggest something for you that fits, and it's not overheating, and it's everything. But my colleague is experienced enough to go completely custom. So what you can see here is leech wire, 180 strands by 71 microns per strand, unserved, 3 insulation layers, so triple insulated leech wire, for example. He edits the exact dimensions of the bobbin. For the secondary, it's again leech wire, triple insulated, with a different number of strands to get the current density, approximately 5 amps per square millimeter right down. And you can see here all the different results once he runs it. Let's just pause right here. Okay. So you can see now the winding arrangement. He selected primary, secondary, primary. And this is actually parallels too, so it's a bifilar winding. That's what you see two. Okay.
Yeah.
So the secondary stands in the middle, which is tightly coupled, okay? You see the space that you have in the bobbin, you see everything. But you can go completely custom. If you hit the customize button over there, you can even drag layers around and see what the losses are doing.
nice.
Like this is going to take to run it. You saw it takes 10 seconds to run every iteration. It's not running finite element method, so that's what you have. And now he has burnt his magnetic. Why? Too high temperature, Curie temperature reached. You see, this is thermal runaway. The losses are too much, excessive. That's because he opted for free convection, and we need forced cooling for this power density to work. So he goes to advanced section, forced cooling, specifying 4 meters per second, and he gets the new result right here, which is workable, very workable for the application. And also you can see a breakdown of the total losses, core losses, winding losses, and also the max temperature. Where is it located? You can see right here. It's located in the center leg of the actual core. So you have a bit of detail what's happening before you measure it in a lab with a thermal camera. And another thing which is very powerful is the prediction of the leakage inductance of the transformer right from this point before even building it. So you can move layers around and see that happening. Also, you see all of the losses are calculated, which losses are calculated for the windings. I mean, core losses, we saw that, but skin, proximity, fringing field included in the proximity effect, DC losses, if any. So that's basically what you will ever need. I mean, as long as it's a good prediction, that's what you need. And basically, the minor things here are you can adjust the coil former as well, which can make a difference thermally, like a significant difference. Depends on how close you are to the gap, because you're going to have fringing effects right there. And you can specify also mechanical aspects of the design. The video is going to just go there in a sec. Or you can even customize your core, as my colleague is doing right here.
Just for my curiosity, what's the insulating material for this? Just enamel?
Insulating where?
So you've got the insulating layer. What material is that?
Insulating material of the leach wire is triple insulated.
Okay.
So insulating material is there are different insulating materials.
Yeah, that's
actually,
what I was wondering. Or is it just?
But it's standard. It's something standard. It's not something that you choose every time.
Okay.
Like, once you go there, you specify varnishing, thermal class.
Wires,
pin out.
Okay. Cool.
But I mean, once you get into details with this transformer, because this is an automotive application, you need isolation. So that's why he opted for triple insulated wires. There is support on the back, like if you go for safety standards, which exact safety standards, how many crimpage clearance distance do you need? Is insulated, triple insulated wire allowed in that standard? All of these questions can be specified on the back as well. And mechanical aspects of the design, easy stuff. It's not that complicated.
So this is the bit that I liked when you showed before, because you could choose all your terminals.
You get basic PDF outputs from that design, and at the end you can order samples. That's the idea before moving into manufacturing high volumes, which we can do. You can move into ordering a couple of samples, have it in a couple of weeks. That's the idea.
Yeah, and just to reiterate that, you'll have samples in a couple of weeks, as opposed to months. So, and fully custom to your needs. So, it's really cool.
And the thing is that it's not just the software. There are power electronics engineers assigned to you once you're a client to help you go through the whole process. Maybe you're an expert on magnetics, but you're not going to be an expert on the tool at first.
Yeah.
And even if you're an expert, you're missing stuff. Having someone to tell you, double question you if you did something, in software and hardware, it's all good. Somebody checking up on you
of course.
Before you order something.
Yeah.
Like, it's always nice. And now it's just ordering the magnetic.
Excellent.
Like that, someone is going to get back to him in a couple of days with, or in a video call. It's human. The interaction is human. Right.
Cool.
That's it.
Excellent. So, in terms of, you mentioned automotive, obviously this is a power supply application stuff. What kind of other applications do you typically see your customers using the software for designing parts?
It's, I mean, the industry range, it can be the medical industry, automotive, space applications
Okay.
as well, or even defense companies, which
Cool.
is another area.
Yeah.
All of these, I mean, they basically design the same things, but the safety standards, for example, are different, the processes are different, the clearances are different, so it's not very intriguing as an engineer, but the standards are different, so you need real attention there to have something that's qualified from the prototype level.
Cool. Well, that was an excellent demo. Thank you very much, Sotiris.
Hopefully it wasn't boring enough.
No, I'm sure for the people who need to know, it'll be very, very interesting.
Okay.
So, but at the end of every interview, I like to ask, how have you found how the show this
PCIM.
year?
Well, it's been my first time in PCIM, so it's like a candy store
Yes.
for an engineer. For a real nerd, it's like a candy store. So
Yeah.
that's about covers it, I think.
Yeah, I'm actually
Too
surprised
much.
at how much I enjoyed just talking about power stuff, because I'm more of a sensors guy, but I've barely gone over the other side.
Yeah, you actually see stuff. You actually see boards.
really
you
good.
actually see hardware, software, like displayed. You don't get that from a website or
No.
You go there and speak to people. It's a different story.
So that was our chat with Frenetic, that's just a really cool little way of doing magnetic stuff. Magnetic simulation, I've had a lot of experience with, and having it in that way where you can just simulate what you want to simulate and then get the hardware out at the end, custom made, then it's kind of incredible. I look forward to seeing how that all progresses. But if you want to check out Frenetic, head to the ipXchange website. We'll have some details about the software, but I think the best thing to do is just follow through on that walkthrough that we did. Really, really good technology. One of my favorites from the show.